So welcome to the Picture Language Seminar. It's November 3rd, Election Day in the US, so we're very happy to have some distraction. And upcoming, we have interesting talks. Next week is Sergei Gukov, and you can see the list behind me for the weeks after that. And today, we're extremely happy to have Liang Kong. He's talking to us from SUSTech, that's the Southern University of Science and Technology in Shenzhen. We had a little problem with the internet connection earlier, but I hope we won't have any more problem. And Liang is going to tell us about on the classification of topological order with finite internal symmetries. Liang, floor is yours.
All right, so let me share the screen. Yeah, so can you see it now?
It looks good.
All right, okay. So first I want to thank Arthur and Xiang for inviting me to speak here. Yeah. As I understood, this seminar is a mixture of physicists and a mathematician, right? So I get the idea from by looking at the speakers, recent speakers. So my talk will be the mixture of mathematics and physics. So feel free to stop me anytime during the talk, okay? So I'm going to talk about a classification of so-called symmetry protected topological order and the symmetry enriched topological order, just briefly as SPD, SED orders, with finite internal symmetry, or sometimes also called finite onset symmetry. All right, so this is it's better to mention at the very beginning among my collaborators. So this work is online and it's already published, but my co-author is Tian Lan and Xiao Gang Wen and Zhi-Hao, Zhang and Zheng. All right, and there's many of the pictures in this PPT were drawn one of my students. Okay, Zhi-Hao. All right, so let me start to clarify for those mathematicians that what is the physical the meaning of these topological orders and SET orders, just briefly. Okay, so what is so-called a quantum matter is a state of matter at zero temperature. A quantum phase is a universal class of the quantum matters, so at zero temperature. Okay, so quantum phase are distinguished from each other by quantum phase transitions. And there are two types of quantum phases. One is gapped and gapless. They are very different. Okay, but this idea of very different perhaps is not it might be misleading. But I'm not going to talk about that in this talk. But we will hopefully talk about that in the future. All right, so we're interested in the special family of gapped quantum. Oh, sorry, what's going on here? I don't know what's. Okay, I don't know what I touched. All right, so we're interested in a special family of gapped quantum phases called gapped quantum liquid. Okay, and this notion was introduced by Zheng and Wen in 2015. So is the quantum? I'm not going to define it mathematically, okay, because I think the definition as to the level of a mathematical rigor is not known. Okay. Anyway, so this kind of liquid phase is called topological order. It is gapped, and the gapped liquid can also have symmetries. In this case, it includes the gapped spontaneous symmetry breaking orders and the symmetry enriched topological orders. That's called SET orders. And the symmetry protected trivial topological orders. Trivial orders is called SPD orders. Okay. For mathematicians, both topological orders and SPD order are special case of SET orders. Okay, because topological order is just SET orders with trivial symmetry. Okay. And SPD order is SET orders with a trivial topological order. Basically, that's the. All right. So sometimes I would just call it the SET order. Treat the other as a special case. All right. So before this work, there are already many results on the classification of SPD SET orders. Okay, but these results are obtained mainly from case-by-case studies. Okay, sometimes even based on the different definitions. But I will just give you some examples. I'm not going to go through the detail because I don't know those details myself. In 2D, for bosonic system, they're classified by triple, and GH is the symmetry group of the Hamiltonian, and the G psi is the symmetry of the ground state, and another, there's a 2-cycle as well. Another for fermionic systems, the classification can be obtained from that of bosonic system via the so-called Jordan-Wegener transformations. Okay, so you can see that the method to obtain the classification is very different. Okay, and in 2+1D, there are two approaches towards the classification. One is based on the so-called G cross the Brady fusion 1 category. Another is based on the minimal modular extensions, okay, of the unitary Brady fusion 1 categories. They're very different, but prove to be equivalent in some sense. Okay. In 3D, there are some results based on the unitary modular 2 categories. This notion is not precisely defined yet. Okay, and the sigma model constructions. 4D, 4+1D example unknown, but classification is unknown. Okay. So the obvious questions you can ask is that, is there a universal approach towards the classification of topological order with symmetries in all dimensions? Okay, that's the natural question, and also is the goal of this talk. Okay, so there are two fundamental approaches towards the study of topological orders. One is the microscopic approach. What you do is that since there is a gapped condition, right? It's a gapped quantum phase. So at the 0 temperature, only thing matters is the ground state. Okay, so this leads to a natural definition of the gap quantum liquid as an equivalence class of the ground state with the equivalent relation defined by this condition called local unitary transformations and the stacking of the product state. Okay, that's the microscopic approach. But I'm not gonna go to the detail of the macroscopic approach because I'm not gonna do that in this talk at all. So I'm gonna do another one, which is called a microscopic approach. In this approach is that you consider the phase only in the long wavelength limit. You consider what kind of observable you can collect at long wavelength limit. Okay, then you can see that they form a higher category. Okay, so this is the approach we're going to take today. So you're going to see a lot of a higher category emerge from the discussion. Okay, why you can see the higher category? So let me give a brief review. Since the topological order is gapped, so as a quantum field theory, all correlation functions decay exponentially. Okay, before the discovery of the topological order, people have the wrong impression that this kind of system might be trivial or boring because all the correlation functions, it's decay exponentially, and in the long wavelength limit, it seems that there's no observables. Okay, but it turned out that a topological order allows non-trivial gapped topological defects. I put a gap here. Actually, they also a low gapless one, so it's making so it's very, very rich. But today we focus on gapped one, okay, for today. So I draw a picture and show you how it looks like. Let's say the A is a topological order and the B is another topological order, okay, and they can connect it by two domain walls labeled by F and G. Okay, this is codimension 1. We also call it the codimension 1 defect. Okay, and these codimension 1 defect can be connected by a codimension 2 defect, which is labeled by the phi. Okay, and so on and so forth. You can consider higher codimensional defects. Okay, these structure exactly form a higher category. So if I draw from a higher category point of view, the zero codimensional thing will corresponding to the zero morphism, which is object in the higher category, let's say A and B, and the codimension 1 defect is exactly one morphism in a higher category, and the codimension 2 defect is the two morphism in a category. Okay, so so I wasn't able to draw the higher dimensional pictures, but you can use your imagination to imagine that there are higher codimensional defects, and they form the higher morphisms in a higher category. Okay, I won't give a precise definition of the higher category because well, it's not so relevant to my talk. It's just to get to the intuition obtained from this higher codimensional defect is good enough, I think. Any questions about the statement?
This is rad. So physically, what do they correspond? These defects and higher order defects, or the
So what? Well, I can give you only one example. Let's talk about this in one example, maybe. No, that's the next two slides. So do I have a well, I have to think about what are you a physicist or what
yes,
what?
I'm a
Okay, so do you let's say do you familiar with the torical model? That's a typical one. So in that case, you will see in that case you will see anyons. Those anyons are codimension 2 defect.
Okay.
Right, because they're point-like, right, living in a plane. So they're two-dimension, codimension 2. In toric code, you can also have a gapped domain wall, which is codimension 1. Sometimes the gap domain wall is invertible. We're gonna come. I think we're gonna come back to that in the next 2 slides.
Okay.
So I will further explain that in the next 2 slides. But for now, just keep in mind that the higher category have some kind of zero morphisms. Okay, have some zero. So the basic structure of higher categories, it has zero morphism, which corresponding to just topological orders. Topological orders, and they just label topological orders. Okay, label topological. One morphisms are codimension 1 defect, and 2 morphism defect codimension 2, and so on and so forth. Okay, so yeah, we just keep that in mind. All right, this become a little start to getting a little abstract.
I was hoping I could ask also a question related to the previous slide.
Okay.
So are you saying that because earlier a few slides ago you said something like certain definitions are not yet rigorously mathematically defined. Are you saying that we would like topological orders to form a higher category, or are you saying we actually have examples of higher categories whose objects are mathematically rigorously defined and encapsulate some notion of what we call a topological order and topological defect? Which of those two situations are being captured here?
I think there are examples. The very concrete lattice model that you can see that how higher categorical structure emerged from it. But in order to be rigorous, the only thing I know so far are you can realize 2 categories. The only example I know is the higher one is 2 category. 3 is how, if you give me a 3 category and ask me how to realize it in the concrete physical models, I don't really know. But for 2 category, only recently people read it up. Let's say, for example, the 3D torical model. 2D torical model is well studied. That's well known. You can see how the categorical structure come out of this. But for 3D, there are some works by arXiv Boulevard, but that's a little bit hard for physicists to see. We wrote another paper on a 3D torical to tell you how the 2 categorical structure emerged from this. That's the only thing I know. I'm not so familiar with the physical literature, but I think that's the only example. For higher one, I don't see any rigorous.
Most of the higher morphisms are basically isotopies. So these two
But they,
categories. Go ahead.
no, you can, I mean, higher defects. So for, let's say 3 + 1, you can have surface defect, you know, like a membrane defect. This can be constructed in I think there work to construct that. Yeah.
Okay.
Yeah. All right. So let's move on to the next slides. So let's consider the special situation when A equal to B, and when A equal to B, that just means that then the Hom space. So I label the Hom space here. You know, the Hom AB represent all the domain walls between A and B, and the domain wall between domain walls. Okay. Now, when A and B equal, when A, B are equal, this looks like a defect internal to A. So that should be viewed as some kind of intrinsic structure of A. Okay, of a topological order A. So here's I'm showing that. So when A, B are the same, the Hom space, I will label that as omega A. Okay, and in this omega A, there is a trivial defect called trivial domain wall. I will label that as 1A. Okay, in this 1A, you can further consider the domain wall between this trivial domain wall. Okay, you can have omega A2. I'm going to show you that in the next slide.
But what is a trivial domain wall? Does that mean
okay, yeah. So here I will give you one examples. So in the 2D topological orders, okay, in 2D topological orders, you can have, so this is labeled A, okay, you can have codimension 1 defect, all right, and the X is a codimension 2, all right, and this 1A is the trivial codimension 1 defect. I'll just label as using the dash line, okay? Now you can have the, well, so if you use the dash line or nothing to label the trivial domain wall, you can have a non-trivial domain wall between two trivial domain walls. That's exactly the particle in the plane. That's A, labeled by A here. A is a non-trivial domain wall between two trivial codimension 1 domain wall. Can you see that? And this one, 1A, well, this notation a little bit weird. So if I use 1A to label the trivial domain wall, I can also use, again, 1 of 1A to label the trivial codimension 2 domain wall connecting this trivial domain wall. That just means nothing there. So this corresponding to the trivial particle. So this is trivial particle. Okay, so in this case, anything codimension 2. What?
You never explained what it means to be trivial.
Trivial just means, okay, so how to see there is a domain wall. So let's say there is imagine A is a chunk of material. You fold A along a line, along the dash line here, okay? You fold A, you just fold like this, okay? Then you create a gap boundary. That gap boundary is precisely a trivial domain wall between A and A.
But I guess if you had a physical piece of matter, let's say a lattice, right? Then like a quantum algebraist would, for instance, associate a C-star algebra to like each lattice site. They would take, you know, the tensor product of over lattice sites. What mathematical object is at this boundary that you're describing when you made this fold? Is it a linear map? Is it or what? Yeah.
Maybe I just don't need to fold it. In the lattice model, let's say I just in the lattice model, I will pick out a region along a line. I just claim that's a domain wall of can be viewed as a domain wall of two sides, connecting two sides. That's called a trivial domain wall. Just any line in the lattice model or neighborhood of the line. Yeah. If I want to create a non-trivial domain wall, then I will fix the Hamiltonian or fix the local degree freedom around the in the neighborhood of the line. I will maybe add more things, and maybe I will change Hamiltonian there to make it a non-trivial domain wall. But for trivial domain wall, I just do nothing. I'll just
here I'd
Does
like to
does
make
that answer the
a
question?
little bit of comment. That's
Oh, okay.
there's
Yeah.
yeah, there's a way to create a little bit of non-trivial domain wall. That is, if some extension along a line can be created by local operator along the line, then this local operator only creates so-called trivial domain wall. The non-trivial domain wall is some line-like object which cannot be created by line-like operator. It's a so this is that's another distinction.
Yeah.
Physically, one can say that all the extension is something can be trapped by some potential, and however, a trivial domain wall means that you can turn off the trap potential without closing energy gap. So there's a smooth way to turn off trap potential to nothing, and everything evolves smoothly. And this kind of trap extension would be called trivial. If you can turn off trap without encounter any singularity. So there's several ways to define that. But I only know about the physical way. The mathematical way may be a little tricky.
All right. Oh, thank you for the comment. I have 1 hour, right? So I probably need to speed up a little bit. All right. So let me say it again. So a particle in this 2D, 2+1D case, what I draw is a spatial dimension. Okay. This is 2 is a spatial dimension here. Okay. So a particle is codimension 2 defect. Okay. This codimension 1 is a domain wall. Now in 2+1D case, if you just count the particles, okay, like this, the count the particles, they can be fused. So there is a fusion. Okay, they can be fused. It's just moving 2 particles close together. They can be braided. For example, you can move a particle around another particle. So it's called braiding. If you put all this data structure together, that you get a unitary modular tensor category. That's a very mathematical terms. I'm not going to explain it. It just catch the mathematical structure of a system of anyons. Okay, in a plane. Okay, one point is important in this notion is that the double braiding is non-degenerate. What this means is that you can put a particle B in a plane. Then you use another particle A to detect it. How to detect it? You just braid it, okay, around the B. Okay. Then this non-degeneracy condition says that if you do a full circle, that's just mean double braiding. So I express it here. You can braid it twice. If you see nothing, if you detect nothing, then it just means double braiding is trivial. Okay, it's equal to the identity. Double braiding is trivial. But if the detector A, if your detector run out all the possible detectors, okay, then if this is still trivial, that means you just couldn't detect it. Then B must be trivial. Okay, B must be trivial particle. By trivial particle, I mean it must be direct sum of the trivial particle. Okay, so this is called a non-degeneracy. We're going to use this in the future. The second point I want to make is that, okay, this is only the particle. You can add all the codimension 1 defect, okay? And that just means you have to add all the F's and all the G's. They form, oh, sorry. Then they form a fusion 2 categories. Why? Well, you can imagine, right? The codimension 1 defect are 0 morphisms, and the codimension 2 defect are 1 morphisms, and the codimension 3 defect, that's the defect in the time axis. I didn't draw the time, okay? You can also insert defect in time axis, that's the instant time. Then they form a 2 category. It's called sigma m. It's a very deep thing here. I'm not gonna explain that. It was totally clarified by Douglas Reuter and I forgot to say Gaoto and Johnson Fried. In a very nice paper to explain that was so-called, mathematically it's called a delooping of M. I'm not going to explain that, but it just intuitively you can see that they form a monoidal structure because you can fuse 2 codimension 1 defect horizontally, right? This one, you can fuse this one and with this one. All right, so that's just give you monoidal structure. Another missing structure is, I don't know what's going on here. Another missing structure is chiral central charge. I'm gonna ignore that for this talk because it's not so relevant. All right, so because of that, then, okay, I wanna, okay. The only point I wanna make is that these, together with the chiral central charge, you can determine the A completely by this M or by sigma M. What does this mean? This means that you can describe a topological order by the internal defects inside the topological order up to something. That's called up to a central charge. Okay, I will ignore that. I will just focus on this. Okay, focus on this part of the description of the topological order, which is given by topological defect. If this is true, then it's only reasonable that SPT, SET order can also be similarly described by its topological defect up to so-called invertible topological order. This invertible topological order in this case is exactly captured by a chiral central charge. I'm also going to ignore that. So what is an invertible topological order? Invertible topological order, it can be viewed as, by definition, it does not have any topological defect in it. Okay, that's invertible topological order. This is something that we cannot see from topological order. All right. However, this idea soon runs into problem. We will illustrate the problems, okay, in this 2+1D SPD order. What happens? Well, because in a 2+1D SPD order with symmetry G, there's no non-trivial topological excitation because it's SPT. SPT means it does not have a topological order. Okay, so the only excitation it can have is the local excitations that carry symmetry charges. Okay, so you only have symmetry charges. What is symmetry charges? These are G representations, okay, of a certain group which define the local symmetries, on-site symmetries. So these symmetry charges form a category of the G representations. All right. For bosonic case, it is Euro rep G with the symmetric gradings. Okay. For fermionic one, for fermionic system, the fermion parity counts for the number of fermions. So exchanging two fermions give a phase factor -1. These give another braiding structure called a fermionic braiding structure on this same category. Okay, the same category can have different braiding, depends on whether you have fermion or not. So in order to distinguish them, we will denote the category rep G equipped with the fermionic braiding structure by rep GZ. Okay, this is standard math notation, but not so often used in the physics literature. I apologize for that. Okay, but in both cases, it can be summarized by so-called symmetric fusion 1 category, because by a famous theorem by Liang, he proved that any symmetric fusion 1 category is either rep G or rep GZ. Okay, so you can equivalent to say given the finite on-site symmetry G is equivalent to say given the symmetric fusion 1 category E. That's the same. Okay. All right. Oh, here then is the problem. Since the SPD order cannot contain any topological excitation because it's topological trivial, right? It's corresponding to trivial topological order. It does not have a topological excitations other than the symmetry charge. Then we should expect that there is only one SPD order because it either described by rep G or rep GZ. There's no other choice, it looks like. But on the other hand, it is well known that there are many 3D SPD orders classified by 3 cohomologies, 3 cocycles, okay? And if you have a fermion parity symmetry, it's classified by famous Kitaev 16-fold way. So what's going on? This obvious contradictions, right? So the contradiction tell us the description of the SPD order by symmetry charges alone is incomplete. So the natural question is, what are the missing data? Okay, so today I'm gonna introduce two ideas. Okay, we need some new ideas to figure out the missing data. One is gauging the symmetry. Another is called boundary box relation. We start from the gauging the symmetry. Okay, so the gauging the symmetry originally was introduced by Levin and Gu in a 3D SPD order. So basic idea is this. So the original symmetry transformation are global. By gauging it, we introduce a G gauge field coupling to the Hamiltonian. As a consequence, the original symmetry become a local symmetry of the gauged field. The new Hamiltonian realized 3D realized a 3D topological order because the symmetry is broken. Okay, they realized the topological order, and the topological excitation of the gauge theory include both the symmetry charges and the gauge flux. By gauging it, you adding a new topological defect in it. That's called the gauging flux. Together,
Excuse me.
they form a unitary multi-tensor category.
There's a question.
Yes.
Who's talking?
Well, Freddy from Zurich. I think this idea of gauging symmetries goes back to the 90s, and I thought I had introduced it, but apparently that is not known anymore. That's just a comment.
I see. Yeah, I think you're right. This gauging the ideas have a long history. I probably should add more reference on this. Yeah.
All right.
Yeah, that's a good point. Thank you. All right. So then the different SPT orders are distinguished by different gauged series. You can gauge the series in a different ways. For example, in the G equals Z2, Levin and Gu show that one gauge series is Z2 topological order. When after you gauge it, it just ordinary, that's a Torrey-Code models. You can realize that. And the second one is double thermia. Okay. All right, I think that's it inspired by this work, by this idea. Lan, Tian, Xiao Gang and I introduced the categorical formulation of the gauging process. So how to formulate categorically. Given the 3D SPT orders, okay, we know that the topological excitation are symmetry charges for now, right? There's no addition, anything else, which form a symmetric fusion category, which is either rep-G or rep-GZ, okay? Now, when we gauge the series, we need to add gauge flux, right? By gauging the series on the particle side, it's just adding the gauge flux. So what we do is that we add additional particles, which is corresponding to the gauge flux, until it form a modular tensor category. Okay, adding more until it form a modular tensor category. Okay, which will describe a 3D topological order, which is called a gauge series of the SPT order. So it means that we got a pair. Okay, we got a modular tensor category, and we got an embedding of E inside M. Okay, that's the pair. And we will be called the modular extension of E. Okay, modular extension of E. However, this is still not right, because not all modular extensions describe gauge theory. For example, given the gauge theory M, we can always stack it with topological order N. Okay, we can add another layer drawn in this picture. We can draw another layer. Okay, now we get a M, and we put another layer. It's still a modular extension. It does not, if the N is arbitrary, it does not describe any gauge theory. So what we need is a minimal condition. We need a minimal condition to get rid of this situation. So what we do is that we require any additional particle Y. If you want to put in additional particle Y, it should have a non-trivial double braiding with at least one symmetry charge. Okay, this condition excludes the Z particle in the bar picture. Okay. Excludes the N. You cannot add this N layer anymore by using this condition. All right. So this requirement is equivalent to say that if a particle has a trivial double braiding with all symmetry charges in E, then Y must be symmetry charged itself. Okay. So in mathematics, this topological excitation in M, which have trivial double braiding with all symmetry charges, form a subcategory. It's called the Muger center. It's just a name for describing the same thing. So then this condition simply translating into a mathematical term. It says that so the minimal condition can be equivalent formulated as the Muger centralizer equal E. This statement is equivalent to say a particle has a trivial double braiding with all symmetry charges E, then Y must be a symmetry charge. Okay, this is a mathematical translation. All right, a modular extension satisfying this condition is called a minimum modular extension. We're going to use this condition. Okay, so then we get a characterization of the 3D SPT order. Okay, up to invertible topological order. It says that 3D SPT order with symmetry given by a symmetric fusion one category E is described by a minimum modular extension. Okay. which is corresponding to a pair, which is a modular tensor category together with the embedding of E. Okay, and this M describes the unitary UMTC of the topological excitation of the gated theory. Okay, so that's the description of also the classification of 3D SPD order. And we denote the set of all minimum modular extension by this set. Okay. Well, this is the abstract theorem. Well, we need to check whether it's corresponding to our known result in the literature. Okay, so because there are previous classification of the 3D SPD orders. So here's the theorem. We prove they're compatible. Okay, so for any fusion 1 category E, you count the set of a minimal modular extension. That's equivalent to say the set of SPT. Okay. It has a group multiplication given by the stacking of SPD orders. Okay, that's physically is known. There is a mathematical stacking given by some kind of a box tensor product in category. I'm not going to write it down, but it can be mathematically well defined. Okay, so the unit of this group is very funny. The unit of this group is the trivial SPD order, which is given by the dream field center of E, and it turned out that the symmetry charge can be canonically embedded in this dream field center. The dream field center of E is automatically a modular tensor category, so it provides a minimal modular extension. So that's very interesting. So given the symmetry fusion 1 category, compute the dream field center. It always corresponding to a modular tensor category. Always give you the minimum modular extension. Okay, so this obvious one, the canonical one, it turned out to be the trivial SPD order. Okay, we're going to use this a lot. Okay, so in particular, it means that given this modular extension is never 0. Okay, so given the E, there are always SPT associated to it. That means that. Okay, now if the symmetry is bosonic, that means E is the rep G. Okay, if this is bosonic, then we recover the well-known group cohomology classification of the SPT, because this MEX, this group is isomorphic to this the group cohomology group. They're isomorphic. And for fermionic parity symmetry, let's take Z2. It simply recovered the Kikov 16-fold way. Okay, so we should be happy. We recover the previous known results. All right. Any questions before I move on? Okay, so that's we recovered all the results. Now we can we can develop the idea further without going into the detail. I just tell you that the main idea of the gating symmetry can apply to STET orders. What's SET orders? SET order is more than SPT. So similar to the SPT, you also have symmetry charges, but you have additional particles. Okay, I will use additional particles outside the symmetry charges. Okay, okay, but now these still have problems. Okay, you need to gauge it. How to gauge it? By adding gauge flux. So you need to add additional particles. Okay, which is called gauge flux to gauge the symmetry. Okay, so that means you need to add certain particles. Okay, outside the E and C. Okay, that's inside M. Add gauge flux which have at least non-trivial double braiding with at least one symmetry charge. That's the minimal. That's the minimum condition similar to the previous one. Okay, so this idea carry on. We can find the mathematical description of SET. Okay. And then you can even do this for higher dimension one. Okay, so for higher dimension one, you can introduce a higher symmetry defined by unitary symmetric fusion N category. I'm not going to define it. What is the N category is, but typically you can mathematically is corresponding so-called N rep G. So the higher representation of the G. Okay, this can be mathematically well defined. Okay, let me just take that as a symmetry, higher symmetry. By gauging the symmetry, give a minimal modular extension, something very similar. So that just means you extend the category by a bigger one, which is called a modular N category. Okay, and the symmetry R is embedded in it. It's very similar to the 2 plus 1D case. It's almost entirely similar. Okay, M is called the unitary module N category without giving the definition. Let's not worry about the definition for now. Okay, but only example I can explicitly know is in 4D. Okay, 3 plus 1D. Every D here is space-time dimension. The minimal modulus tension of 2 rep G are associated to each Fourier cycle have been constructed explicitly. That's the only thing know rigorously. But for higher one, we only have speculation. We don't have a rigorous results. Okay, but that's our the blueprint for higher category theory for higher dimensional cases. Okay, well, this looks very abstract, but we don't need all those things. We only need one canonical one for the later part of my talk. Is the canonical minimum modulus tension is exactly given by the dream field center of R. So remember, R is the symmetry. Okay, it's the higher symmetry. Now you take the dream field center of that. This gives you a minimum modulus tension. It's the same as the previous case. Okay, and it has a canonical embedding of symmetry charge. So symmetry charge R is canonically embedded in this modulus tension, and this one will serve to be the trivial SPT order with symmetry R. Okay. Did I lost you? In the previous case, R is just the rep G, but now replaced by N rep G. Okay, very similar, I would say. Yeah. Okay, any questions? All right. So although the idea of gauging the symmetry works well.
Question: can you map onto some concrete examples so we have something in mind?
Maybe just keep this example in mind. The higher dimensional one is just let's recall this one. Okay, so this one just says that you have a symmetry E that's given by symmetry charges. Symmetry charges are rep G in bosonic case. Rep GZ is the fermionic case. Okay, these are symmetry charges. Now you add additional particle, which is called gauge flux. Together, they made a minimum modulus tension. Okay, together they form a unitary modulus tension category, which is M, and in which the symmetry charge is embedded in it. Okay, for higher categorical case, it's similar. So you have a fusion N category E. Okay, and this is just example of that is N rep G, N rep GZ. Okay, now you consider minimum modulus tension, you still got M and the E is embedded in it. All right, that's. Would that be better?
Yeah, so maybe I can say that in another way. That is, in higher dimension, the symmetry charge are still described by group representations. When you do this modular extension, you get a topological order, which is actually the gauge theory of same group. So it's really gauging. So for this, my understanding for this dream field center is a kind of gauging is like a it's like a gauging. It's give you a gauge theory. So therefore, when you gauge the symmetry in higher dimension, you get the gauge flux line or flux sheet dependent on dimension. So that's additional extension you'll add.
Yes.
Thank you.
Yeah, thank you for the comment. Yeah. All right. So these are very parallel, but okay, you see the idea of gauging the symmetry works well, but it still has some problems. We cannot claim that we have found the missing data because SET order is a well-defined notion before we gauge the symmetry, right? So the gauging symmetry is only a way to reveal the missing data instead of a direct description of the missing data. There should be a mathematical description of SET order without gauging the symmetry, all right? The second point is that if SET order cannot be gauged, then it is anomalous. In this case, this idea will not work anymore. Okay, so in an unpublished work, Dreamfield constructed example of Brady fusion one category, such that the minimum modulus tension does not exist. Okay, so you cannot always gauge it. Then if you cannot gauge it, how are you going to study this thing? So this idea failed in this case. Okay, so but this is also the point that a new idea come out in physics. it was known that an ND-SET order can be gauged if and only if it is one-dimensional higher Bach is trivial, or SET order can be does not have a 't Hooft anomaly if and only if is one-dimensional higher Bach is the trivial SPT order. This is the very crucial idea. So this leads to another approach based on the idea of the boundary Bach relation. Why you need that? Because you see, you need a one-dimensional higher Bach. So that's why you need a boundary Bach relation. Okay, I'm going to explain that now. So first I want to say that, oh, sorry. There's one principle we proposed in 2014 is that each ND topological order has a unique Bach, which is a n+1D, I forgot to put anomaly-free topological order. I should put anomaly-free here, sorry. As a consequence of this, we later proved that this so-called boundary Bach relation simply says the following: the Bach is the center of the boundary. Okay, just keep this in mind. The Bach is the center of the boundary. I draw a picture. So the boundary have a topological order, and the Bach is given by the center of. You probably want to know, what do you mean by center? This boundary is a physical concept. The Bach is a physical concept. What do you mean by center of that? Actually, you can even make sense of this notion in this vague sense, because the notion of center does not rely on the mathematical structure you are dealing with. It only depends on the categorical structure, how you define the relation between the objects. Then you can define the center. You can prove the statement in a very abstract way. That's exactly what we did, without even knowing what the boundary is, without knowing what the Bach is. Okay. However, for this talk, I will give you a more precise mathematical definition of this description of the statement. It turned out that the braided category of defect of codimension 2 in the anomaly-free topological order with a gapped boundary. Remember that for codimension 2 defect, you can always braid the codimension 2. Okay, codimension 2 you can braid, but for codimension 1 you cannot braid. Okay, for codimension 2 you can braid. All right. If the topological order have a gapped boundary, the gapped boundary, it can have a monoidal category of defect of codimension 1. Okay, the boundary have a boundary defect on the boundary, defect on the boundary. Okay, they form a monoidal category. Okay, they form of codimension 1. They form a monoidal category. Now you take the monoidal center of it, then you recover those codimension 2 defect in the Bach. All right, let me restate it. Okay, in the ordinary order. So braided tensor category of defect of codimension 2, at least 2, in an anomaly-free topological order with a gapped boundary is given by the monoidal center, or so-called Drinfeld center, of the monoidal category of defect of codimension 1 in the gapped boundary. Okay, if you want to make the Bach equal to center statement more precise. All right, so you can, well, the detail can be ignored. Just remember the Bach is the center of the boundary. Now we are ready to find a mathematical characterization of the 3D SPT based on the idea of the boundary Bach relation. Recall that the 3D topological order can be described by a unitary multi-tensor category M, and equivalently by a unitary fusion 2 category. Okay, that's something we discussed at the very beginning. Okay, which the sigma M include all the codimension 1 defect. Okay, I use the condensation completion. Probably I shouldn't use it because that's the name where the name come from. Because all the codimension 1 defect can be condensed from the particle defect. Okay, codimension 1 is obtained by codimension 2 by condensation. But we don't need that. Let's just assume. Just to remind you that the sigma M include all the defect codimension 1. Okay, that's enough. All right. Similarly, the symmetry charge is given by E. Okay, we repeated many times already. Okay, because of that, we should do the same thing for the symmetry charge. We also do the sigma of E. This is very mysterious. So let me not spend too much time on this. It's very tricky. It's the key point for our progress, but I ask you to ignore the detail. Just treat the sigma E as E, equivalently almost. Okay, but it's a little bit tricky. Why we need it? So basically, what we mean is that E is a symmetry charge. We need to find all the condensation descendant of symmetry charge. This include all the condensation descendant of symmetry chart. And we view the condensation descendant of the symmetry chart again as a higher dimensional symmetry chart. That's the basic idea. Okay, this is tricky. This is very crucial. It's very difficult to understand. Let me skip the detail. Let's just keep in mind sigma E is also some higher categorical symmetry chart. Okay. Now the key idea, let me remind you again, the bulk of 3D SPT order is the trivial 4D SPT order. Okay, this is familiar with this. All right, now we can state it, what's going on. Recall that a trivial 4D SPT order is given with the symmetry sigma E. Because one-dimensional higher, I need to find all the condensation descendant of the symmetry. So the symmetry chart, after adding the condensation descendant, the symmetry chart have higher dimensional symmetry chart now. Okay, it's not just like a point like particle given by rep G. It's given by higher dimensional condensation of the symmetry chart. It's called sigma E. Okay, now the idea is similar to the before. Okay, how to describe the trivial one? Remember, what's the trivial one? Trivial one is the dream field center of the symmetry chart. That's the canonical minimal modular extension. Do you remember? Okay, in which the symmetry chart is canonically embedded in it. Okay. Oh, sorry. So this pair describes the trivial 4D SPT. Now we just need to define and identify the bulk of the 3D SPT with above pair. So how to identify them? We need a braided equivalence, okay? And preserving the symmetry chart, okay? So we need a braided equivalence. Remember, this is coming from the gauging the symmetry. That's just coming from here. That's the trivial 4-dimensional SPT. This is coming from the gauging the symmetry. This comes from the bulk. Bulk is also given by the center, remember, by boundary bulk relation. So these two, this side, the left side and the left side and right side have a very different origin. So this is a very non-trivial condition to require them to have a braided equivalence. Okay, and braided equivalence should respect symmetry chart, preserve the symmetry chart to make the diagram commute. So here is what this braided equivalent is the missing data, and this missing data is living in the one-dimensional higher bulk. It's not in the same dimension. It's living in the one-dimensional higher bulk. Okay. Now in this way, we got a classification because this missing data is a braided equivalence. Is the missing data that it preserves the symmetry charges. We denote all this equivalence by this group. Okay, it's a group. Okay, and consequently, a 3D SPT order with symmetry given by this E or sigma E is classified by this group, right? According to this. But we have two approach, right? We have one classification of the 2D SPT order with symmetry E defined by the first approach where by the gauging the symmetry. The classification is given by the group of a minimal modular extension. The second approach is based on the boundary bulk relation, and it's classified by this group we just talked about, right? Just defined, all right? Now, are these two approaches equivalent? Okay, that's the obvious question. Mathematically, this amounts to show that these two groups are isomorphic S group. Okay, we need to prove that. Unfortunately, we don't have a group. We don't have a proof yet. Okay, unfortunately, we don't have a proof. But I can further clarify the relation between these two approaches in a physical picture. So what happened is that the braided equivalence can be achieved. So braided equivalence between these two. Remember, they both describe a trivial SPT in a one-dimensional higher. I draw it in this picture. This automorphism between two faces can be achieved by tunneling through this face by an invertible domain wall, canonically associated with this phi. Just imagine that there is an invertible domain wall, and this braided equivalent. This equivalence just give a duality between these two, right? So this invertible domain wall realize this duality. You can imagine that you have a particle, you have something on this side, you can push through this invertible domain wall, become something on the other side. And this process is completely invertible because the wall is invertible. Okay, but now you look at this picture. You look at this picture. This is a trivial SPT. of one dimension higher. This is again a trivial SPT of one dimension higher. What's inside here is invertible. This is a this is exactly SPT of one dimension lower. That's exactly what you want. That's exactly the SPT you're looking for. So the SPT corresponding to the phi, corresponding to an element corresponding to the braided equivalence here is completely natural. So each braided equivalent between these two corresponding to domain wall. And then this domain wall exactly is a lower dimension SPT. Okay, so it looks very natural. Okay, I'll skip some detail of the gauging process for the time. All right, then let's see what time I have. Okay, a few minutes. Okay, okay. So so in this way, yes. Maybe can I finish the talk? Then we can take more questions. Okay. So although I cannot prove to you that I cannot prove to you this two I cannot prove the mathematically rigorously to you that these two pros exactly match. But from this picture, you can see that well, it physically is totally reasonable. If it's not correct, we have to modify our physical intuitions. So so we have pretty confident about this conjecture. All right, so that's a 3D SPT. It turned out that this idea can be generalized to all higher dimensional cases, even including including anomalies. Okay, this approach is very powerful. So now I present a much more powerful result. Oh, sorry. Oh, where am I? Okay, here. So for ND, if you have a n+1D SCT order with a symmetry, higher symmetry given by a symmetry fusion n category R, and even with possibly a 't Hooft anomaly, okay, you can characterize it by a quintuple. Okay, here A is a unitary fusion n category over E over R. R is the symmetry. Okay, so I'm well, let me ignore the detail. Let me just tell you what A is. A describing all the topological excitations inside the SET. Okay, that's A. Let's ignore some detail. Then M is the minimum modular extension of R. Okay, minimum modular extension of this R. That means it is a n+1, n+2D SPT order. It could be non-trivial. Okay, this could be non-trivial one. Okay, which determine the 't Hooft anomaly. So if this is equal to the trivial one, remember that the R symmetry chart, take the dream field center of the symmetry chart is the canonical minimum modular extension, which describes the trivial SPT. If it is equal to the trivial one, then it means the 't Hooft anomaly is vanished. Okay, this is describe the one dimensional higher thing. Okay, so now putting everything together, you got the following. So you have A to describe the topological order, SET. It might have anomaly catched by its bulk. So let's check its bulk. Its bulk might have anomaly if this M isomorphic to it. M is the one-dimensional higher SPT. If this M is non-trivial, then this is have anomaly. If M equal to the trivial one, then it describe anomaly-free SET. So you see, this method is very flexible. It can describe anomalous SET. It can describe anomaly-free SET. Okay, so let me just give you a flavor of this instead of a. So my time is I don't have much. Can I go over for like a couple minutes?
Couple of minutes, yes.
Yeah. So in summary, for potential anomalous SED order, using the idea of gauging the symmetry, we obtain a categorical description of anomaly-free SPT SED order, okay, in one higher dimension. And using the idea of the bounded bulk relation to identify the bulk with this one, okay, we give a mathematical description of potentially anomalous, even more general than the previous one, can include gravitational anomaly, can include other anomalies of all dimensions. Okay, let me not present the general result. Let me just claim that. So this is surprisingly unified framework provide a conceptual understanding of many known classification results in lower dimension, which are often obtained in a case-by-case manner. So let me give one example. So maybe in the 2D case, if you just run the machine, just using the abstract nonsense I just talked about in previous slides, and you do the similar thing here, you know, you can easily recover many known results. For example, I can, let me just skip some detail. Let me tell you that 1D case. So in a 1D case, by our method, we say that the classification of SPD order give you this one, right? It classified by this Brady, the group of Brady equivalence, okay, preserving the symmetry, okay? Does this classification give you the known result in physics? Yes, indeed, automatically, okay? So in this case, you can check that this group is equivalent to the Picard group of R by a result by Davidov and Nixik. And from that, you can compute this by other people's work. You can compute this Picard group explicitly. And you can see that this is exactly the H upper 2 cohomology, which recover the old result in physics. And in a fermionic case, when the symmetry is fermionic, you recover this classification, okay? And this classification is obtained by Xiao Gang earlier by using so-called Jordan-Wigner transformation. Looks like a very, case-by-case in a case-by-case manner, because in that case we don't know how to do it universally. In this way, yes, we got the universal approach, and we got the result agree with the physical classification. Okay, all right. So yeah, that's basically our what we did. And for n plus 3D. Our classification go beyond the Euro-group cohomology classification, because the symmetric coefficient n category is much more than n rep G. Okay, much more than n rep G. It's much more than group cohomology. Okay, much more than the group. So we believe that our result can serve as roadmap for mathematicians to join the study. Okay, and the summary and the looks maybe not. I don't have time for. Yeah, these are just repeated many times, I guess. But let me just say this. This is not, well, we obtain a very universal picture of all these things, right? But this is not the end of the search of the mathematical framework. I think it's only a platform for new and better formulation to emerge. So this universal approach is not the end of the story. I think we will find a better one in the future. All right, that's all. Thank you very much.
Well, thank you very much. So
all right.
There are a lot of questions, because what you talked about, the beautiful picture, and now it's really good to try to understand what you know rather than what you think you know. And there the mathematicians could commit.
Yeah. Well, I want to maybe a few comments. I want to make a few comments. So for a higher category, it's difficult in the sense that mathematical definition is not so clear. But in the recent year, there is in the last year, there is a very beautiful work come out of. Let me see. Oh, sorry. Did I give the reference? No, sorry. It should be somewhere. Ah. Oh, sorry. Oh, it's gone again. Oh, Jesus. Sorry. I lost in the many classification. Right here. I think Johnson Fried have a precise mathematical definition of all these notions without unitarity, though. So this is a remark to ask us questions. How much we know these things are rigorous? I think up to well, if you don't want to select any if you want to talk about the weak N category, model independently, let's assume that this can be done. Then the rest of the subtle problem is solved by Johnson Fried, Theo Johnson Fried. And based on the early work, he wrote together with Scioto. These two together developed a theory called the condensation completion, which is certain kind of Karoubi completion of higher category, from which you can define the notion of fusion N category, without unitarity though. The unitarity can be added maybe this week. I will post a paper this week about the definition of these things. We try to give a new definition of, propose some definition, mathematical definition of that. So what I'm saying is that at this stage is very close to be mathematically rigorous, completely mathematically rigorous, up to concrete model for weaker n categories.
Thank you. Actually, I was looking at his abstract while you were giving your talk. And just for the mathematicians, I think this comment might be helpful. So Johnson-Fried seems to provide a definition for a topological order by actually defining what a multi-fusion n category is. And then he gives physical reasons for why this is a good definition. But the point of that paper is to define what a multi-fusion n category is mathematically, and then propose the physical definition that says a topological order should be defined as such a mathematical object. This is what I got from just browsing it for a few seconds.
Yeah.
And what do you identify yourself, Arthur?
I'm Arthur. I sometimes come to these seminars. I'm a postdoc at IHES.
What is your family name?
Oh, sorry, Parzignot. Sometimes that doesn't come up on Zoom for some reason.
I see. Yeah. So I will make a comment about Asa's comment. So yeah, Theo just defined it as defined the notion of topological order by multi-fusion n categories. Yeah. Before that, as a physicist, you probably want to say differently because there is a macroscopic definition of topological order. So in that way, we used to say we classify topological order by fusion n categories, or maybe with a unitarity. But you know, for mathematician, I think you can just take as definition. That's totally reasonable. Yeah.
Right. So this was related to my maybe first question. Because it seems like the physicists use different mathematical objects to construct these higher categories. So I have maybe an embarrassing but very basic question. What is the simplest example of a non-trivial two category that's constructed from some input data, like maybe some physical input data, but corresponding to something mathematically rigorously? That says, for example, it seemed to suggest that you said like you have objects, you have one morphism and two morphisms, and it seemed like the objects corresponded to topological phases, the defects corresponded to one morphisms, and the particles corresponded to two morphisms. So I was curious, what mathematical objects are these zero cells, the objects, one morphisms, and two morphisms? Like, are we given a Hilbert space, a Hamiltonian, and from these data we construct this category? I guess what's going on in the simplest example that you can think of?
Okay, simplest example I can think of is
preferably an anionic case. Yeah, if you can explain in terms of anion, that'll be great.
Yeah, I think 2D Tor-code model is already good enough to show it. And there's another one. If you want to see monoidal two category, you can look at so two simplest case. One is 2D Tor-code, another 3D Tor-code. I think these two examples should already convince you that this interpretation of should be precise. It should be correct.
And is it easy to explain what the objects of your category are for the 2D Tor code?
Okay, for 2D Tor code, you want a two category, right? Okay, so. Okay, so for 2D Tor code, the object is codimension one defect.
And what does that mean mathematically? It is a set equipped with some structure, or like what is it? Is a Hilbert space, a C-star algebra, a linear operator?
Yeah. So it's corresponding to a domain wall in the lattice model. That in that domain wall, in the neighborhood of domain wall, the lattice is slightly different than the rest of the model, and it has its own interactions, like Hamiltonians in the neighborhood, defined in the neighborhood of the domain wall. That will corresponding to
So the objects,
you have let's say you have a lattice model. Okay, now you just artificially change a line in the lattice model by putting some actual degree of freedoms in it and putting a new interaction in it. You know.
so a two-morphism. So a one-morphism is a Hamiltonian.
It's a defect line Hamiltonian. You can say that way.
Let me, before I answer the question, can I ask you, are you a physicist or a mathematician? So I'm thinking about how to answer your questions.
Pretend I'm both.
Oh, if you're, yeah, you were in ICS, so probably, okay. Let me describe it to you in the level 1 model. Let's just give it a try, because that's a little bit mathematical, but if you have a good mathematical background, you probably appreciate that more. So, okay, so let's think about the level 1 model, and which is can be constructed by using a single fusion 1 category. Okay. Okay, the lattice model is written using the data of the fusion 1 category. Now you pick a line in the lattice model. Now you change the lattice model on this line by module category of the fusion. Let's say the previous fusion 1 category you pick is a C. Or yeah, okay. Then now you use the data of a CC bimodule category. You can rewrite. You can introduce a domain wall on that line, and you change the Hamiltonian. You change the lattice model along that line. You change the Hilbert space there. You change the Hamiltonian there using the data of the CC bimodule. Then you can actually construct a domain wall, and that domain wall is exactly one of the domain wall you're looking for in that will give you the codimension 1 defect. And this codimension 1 defect can be fused even in a lattice model, because you can have a CC bimodule. Okay, that will define the domain wall. You can have another CC bimodule, let's say N. The first one is M. Okay, you construct 2 domain wall parallelly, not far away. Okay, from each other. Okay, then you can see from far away on this lattice model, these 2 domain walls simply viewed from far away, they become a single domain wall. So you can even see the domain wall can be fused. That will corresponding to the tensor product in the 2 category. In this 2 category, the zero morphism is the domain wall. So the domain wall can be, because they have a tensor product, right? The tensor product exactly corresponding to the fusion of 2 domain wall. But mathematically, you know, bimodule, CC bimodule can be tensor with another CC bimodule, right? So in this way, I tell you how to do it physically. I also tell you how to do it mathematically. They're corresponding to each other precisely. And the torical model is just an example, a special case of level 1 model.
So are all these things actually written down in Johnson-Fried? The definitions.
Oh, you mean the definition of fusion N category? Or the definition of what?
Yeah, the objects that are coming into the discussion.
Okay, the definition of fusion N category was defined in Johnson-Fried's paper.
Which paper? The 2020?
Which paper? 2020. It's called On the Classification of Topological Orders. That's the title. On the Classification of Topological Orders.
Yeah. So that's where we have to look.
Yeah, here I'd like to make a comment. Actually, there's a physical definition in terms of lattice model of a topological order. And there's a definition of an N-fusion category. These 2 may not exactly match. The physics definition may be more general. That's precisely the central chart issue. And so basically, that's my guess or impression. It's not rigorous. My feeling is that this fusion N category defined so far correspond to topological order with 0 central charge. Means the boundary can always be gapped. There's special topological order whose boundary can never be gapped. This topological order, we don't know, may or may not be in the current fusion N category definition. So there's some physical motivation to generalize this fusion N category definition even further to include the topological order whose boundary are always gapless. So there's a slight there could be slight mismatch. So so my feeling is that there's still a little bit open, yeah. But there's a class topology which are easier, which is whose boundary always gapped. We call the gap boundary topology order. These topology are easier. That maybe classify this fusion N category. And those also this topology order have a exact Hamiltonian realization by commuting projector realization. So all those things may be related. But there are indeed a topology order which are beyond the commuting projector. I don't know, Cornell, do you have some additional comment? That's my feeling, yeah.
Okay, I want to make a comment both to Asa and to your comment as well. So so tomorrow, my collaborator and I will post a paper online. We further polish the Thiel Johnson-Fried paper on the multi-fusion N category. We add a unitarity as well, and okay, that's one thing. Okay, so but for the Xiao Gang's comment, he said that okay, well, you have to add the gapless phase, right? Yes. So in that paper, we try to make a first move to make it rigorous to add a gapless phase, but in a slightly cheating way. But we want to do it in a series of papers. So that's the only first one in the series. It's a little bit too ambitious, but I'm not sure when the second part will come out because we basically want to do all the gapless phase. We don't know how to do that yet, but what we can do in the paper we're going to post this week, we can do the topological part, but it's still conjectural. The topological part of all the topological order, the categorical topological order, including the gapless phase, including all the gapless phase. Oh wow, this might be too well. We probably have to make assumption about conformal invariant and that kind of thing. We cannot claim all the gapless phase because that's maybe too well. Because I know there's some system, some physical systems which is not conformal. I mean, even though they exist, even in the fixed point, RG fixed point, they're not conformal invariant. We don't know how to deal with that. But for all the rational conformal field theory, we can find a categorical way to reconstruct them. Because I want to make a comment is that even though a gapless phase looks very strange, looks very crazy, okay, it's much more complicated than the gapped phase. That's the common impression. But in the recent progress we made with my collaborator, maybe 1 year or 2 years ago, is about how to classify the gapless age of the topological order. Let's say 2+1D topological order, the gapless age of the 2+1D topological order. What it revealed in there is that even for the gapless phase, it still have topological feature. Okay. So why have topological features? Just imagine that you have a quantum gapless phase, and you can still have all kinds of gapped excitations. Those gapped excitations behave like topological defects. Together they should form some kind of categorical structure. So even the gapless phase have topological features that need to be catched. Okay, so. So for example, for gapless age of the 2+1D topological order, we show that it has something called a topological skeleton, okay, which purely gapped thing, which have nothing to do with the vertex hyperalgebra or conformal field theory correlation function. Ignore those things. There is a so-called categorical defect. The category structure capture the information of a topological defect and some additional thing. We call it topological skeletons, which capture all the topological feature of this thing, of the gapped space. And we can show that this topological skeleton, okay, it's perfectly matched with the Bok in the sense that boundary Bok relation holds. You take the topological skeleton, which is a categorical, which is an enriched category. You take the dream field center of that. You exactly recover the Bok, which is 2 + 1D topological order. So in a sense that we feel that there is a universal framework, a universal approach towards all gapped space. That's the comment I want to add to Xiao Gang's comment. So hopefully we're in the age to study gapped space now.
So thank you very much, Liang. We really enjoyed this. It's
Thank you.
an interesting subject with many open questions, which we hope will be resolved. And it's fascinating to have all this discussion. So
Yeah,
thank you again. And I think
Thank you very much.
meet again next week.
Thank you, everyone.
Thank you. Bye-bye.
Bye-bye.
Thank you.